and turn on the heater. Can you imagine? Your freezer has a heater inside. It's super hot. You can even see that. It's at the bottom of the freezer on the back. Whenever the heater is turned on, it turns red. It's a red color. It's red hot. It's a heating bar, heating up the frost to melt them. That's how that works. I didn't imagine. I was thinking, if I have such a heater in the freezer, is that going to affect the effectiveness of the freezer? Actually, it's not. It's just turn on the heater, heat up the frost, and thaw it, and turn off the heater. That's it. You can still have a freezing cold ice cream put in the freezer, no problem. So here's the issue. The heater is not working anymore. So the frost is not going will build up every 2 weeks, and I don't know if the heater will be turned on or not, since I couldn't see that. It's inside the freezer, and I don't know when it's going to be turned on, because it will only be turned on after a period of time, and I don't know how long or how soon. So I couldn't just open the freezer's door and sitting there and looking at that one and see when it's going to be turned on. Right? I couldn't do that. So how can I fix it? So there's a mechanical switch. It's mechanically being attached or released. So when it's attached to the metal, it makes the connection and turns on the heater, right? So I was thinking, hey, it's a mechanical switch, so there might be something wrong. It can worn out really quickly, or not quickly after a few years, because it's mechanically turning on and off, right? So that's where the starting point is. And also maybe the problem is the temperature sensor. So I ordered online, I ordered a temperature sensor, I received it. But by looking at the temperature sensor, everything has been wrapped up in a rubber case or something. So it's not really fragile. So I'm thinking the chance of the temperature sensor is going down is really slim. So it must be either the heater, or because the heater is being heated up a few times a day, maybe it's being burned down or something. So the heater maybe, or the mechanical switch. And there's a really easy way to test the heater, which is you take it out and you measure the resistance between the two terminals. The heater is nothing but a resistor, a huge resistor, and it just allows the electrical current runs through the heater, so it's converting the electrical energy into heat. That's it. So if that one is burned down, which means if you measure the resistance on the two terminals, you are getting nothing, or you are getting a huge resistance, because it's probably being burned down in the middle, so it's getting disconnected. So you are not getting any resistance. Okay, and I measured it. It's something around 50 ohms, which is pretty correct, because you do need a low resistance to allow more current run through that resistor. So the heater is fine. So I was thinking it must be the mechanical switch, and I just grabbed it. I dismantled that from the freezer, and I looked at the mechanical switch. It has a bump on the top, so it must be broken. So I finally found the problem. I replaced the switch and put everything back and start working. So if you know how to deal with all these things, probably you are not going to debug really complicated issues in the freezer or somewhere else in microwave. But at least you have a multimeter at home, and whenever you need to measure the resistance of the heater, you can measure it and you know what's going on. So that's one thing. Another thing is my HVAC for hot water. So that HVAC has a little temperature sensor as well. So it's measuring the temperature, so it can turn on, turn off the heater to heat up the water. And that one is disconnected. So I, figure out the problem and replace the thermocouple, which is a temperature sensor in the HVAC, and made it work again. So that's two examples. There's another one I forgot. Oh, there's a motor in the HVAC as well. That was the first time I had a problem in my house, and I was not trying to fix by myself. I asked for a person to come over in Durango, and that was a 2-hour labor, and he asked for $700. That's also the motivation for myself to DIY everything at home. That's just like ridiculous. 2 hours, $700, including the material anyway. So the little motor to blow the air into the HVAC. But anyway, since I was not thinking to do it by myself, because right now I'm used to that. In the future I'm going to try to fix everything by myself. All right, let's start the lecture. And for the ones just came over, I'm telling everybody in the class that I'm going to run the lecture for about 1 hour, 50 minutes to 1 hour, and I will split the entire class into several groups, so 2 or 3 students per group, and I will give you a quiz, and you are going to work on the quiz within the group, and I will use a little random number creator to pick up which group will present in front of the class to everybody for the solution for the quizzes. Okay? Not one group, probably 2 or 3 groups present different problems on the quiz. All right. So first of all, okay. I'm recording this lecture and I have notes written on the paper. I will scan my notes into a PDF format in one PDF file, and I'll upload the video and the notes to my website. Do you know where's the website? Electronics.com. So you can see videos and notes over there. So after this class, you can still watch the video and look at the notes to prepare for, we don't have exams, prepare for, I don't know. We don't have exams, do we? Probably don't have exams. We only have one final project. Okay, so we only have quizzes. Quizzes, okay? All right. Electrical currents. Voltages and currents. Am I blocking your view? A little bit? A little bit? This will be better? Okay. Let's do this. All right. Voltages and currents. So you have been using batteries, right? So a battery like this. That's plus, that's minus, that's anode, that's a cathode. And it's labeled as 1.5 volts as the voltage rating. And the symbol, if you're using a circuit simulation or analysis software, you're going to see something like this. Or in a class, we're going to draw a battery like this as a DC battery. So DC battery is a steady voltage, it's not changing. And for a battery like this, there will be a lot of positive charges accumulated at the anode and negative charges accumulated at the cathode. And if you connect the battery to some external circuits, what's going to happen? So what are negative charges? Have you heard electrons for the rest of the class? Electrons? Have you? Electrons? Electrons. Yeah, I've heard that. You? There? 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 What is the electron? What is the one electron, or what are electrons? Part of the atom, right? So let me see if I can still remember this. So for example, the hydrogen, how many electrons? Outside electrons? 1, right? So here's a core, here's a outside layer electron, only 1 electron. And so that's why it's if this if this atom loses this electron, it becomes a ion. Couldn't remember the English name for that. Becomes an ion. That's how that works, right? So that electrons, atoms. So the electrons of the atoms. So the electrons can lose. The atoms can lose electrons if they are conductors. So the wires are metal conductors. So they are really easily lose the electrons at the very outside layer. Just remember that. So for example, copper or any other aluminum, the metal, will lose the electrons. If you have electrons accumulated at the cathode, and you have a positive anode terminal as well, because positive will attract negative, right? So this anode terminal will attract electrons to this terminal. That's how that works. And we use this as electrons, so the electrons will flow in the wire. It's going to flow like this to the anode. Okay? And this forms what? Electrical current. However, we define the direction of the current in the opposite direction of the to the direction of the electron. So electrons move from where to where? Negative to positive. So the current flows from positive to negative. That's current, which we use I to represent that. So that's the current direction is from positive to negative. Only when you have a wire. If you don't have a wire, what's going to happen? No current, right? But still have what? You still have charges, and then you still have a voltage difference. So here are the different terms. Okay, charges are the real particles. You don't have positive charges, right? So there's no positive charges going to flow in the circuit. So they are just the atoms or the ions or atoms just lost their electrons, and so they become ions. But whatever is actually flowing, you can say flowing in the wire, in the metal, can only be electrons. Make sure you understand this. Never make any mistake like this. So you tell people positive charges are flowing. No, never say that. It's always electrons are flowing, and we define the current, the direction of the current to the opposite direction of the electrons flow direction. Sorry for my English, but you understand what's going on here, right? So electrons flow in that direction. We define the current flow in that direction, but actually there's nothing flowing in that direction, which is defined. We define that's the current direction. That making sense for everybody? Yeah. Okay, great. So charges are the particles or electrons. What are voltages or voltage? What is a voltage? Volts. Sometimes you can see volts. So if you have charges accumulated on two terminals, you'll get we call it a potential difference or voltage difference. They are just concept definitions. You guys are pretty new to this. Feel free to ask any questions, but actually you are forming this kind of concept in your mind. So it's fine to feel like it's challenging or something. Is just feel free to ask any questions. If you have charges accumulated on two terminals, you get a potential difference, and we call that potential difference as voltage. So similar to real life, which is gravity potential. Okay, If you stand on a, for example, stand on a table, you get that potential. So you can jump from the table, you'll fall to the ground. Okay, so get that potential. That's energy. Is that energy? If you stand pretty high, do you have some kind of energy? It's a potential for energy. Yeah, that's correct. Good point. Because if you jump, you have energy, since you have a speed. And you have a mass, right? So you have some kind of a weight. And weight, speed will be converted into energy. I understand you probably haven't learned physics, have you? But do you understand if you have a mass, if you have a speed, you are going to have energy? Do you know that? Think about that. Because energy can be transferred or be transformed to another form. You are thinking, you doubt if you have energy when you are running. You can think if you can transfer the energy to something else. If you can, then you can think about that. You have energy. When you are running, can you transfer that energy to something else? When you're running, yeah, you can push something. When you're running and you see something, you push it, then that one will keep moving, right? And that one, for example, or if you are manually move a turbine, you can convert that kind of magnetic field. When that metal is cutting the field, you can convert that one into electricity. So which is how the generator works in the power plant. But that everything converted from your muscle. So when you are moving, actually you got energy. Okay. Anyway, that's too far away from this, but you get that voltage difference, and you have a potential to deliver energy to the outside world for this battery. Why? If I have a battery, here's a battery, for example, cathode anode. Okay. We don't need to care about what's going on inside. It just has two terminals. And when you are using this one for your little toy, okay, for example, you put it into your little car, it's gonna start running, right? Turn on the switch. You can keep the car running. Why? Because that battery is converting the chemical energy into electrical energy. It's converting that chemical reaction to the outside world. So it's creating all these positive and negative charges, the two terminals. If you do not insert this one into the toy, it's not working, it's not doing anything. But however, if you put it into the toy, it forms a circuit which will connect the two terminals in some form, will allow what? Flow to where? What? Yeah. Will allow current flow from positive to negative, or will allow electrons flow from negative to positive. Okay? That's how the electrical power is being delivered to the circuit. And you can power up an LED, you can power up a motor, you can power up everything, just because you have what? Current being delivered by the battery. So the current is actually the real thing, flows through every component in the circuit. Why do you have current? Why do you have current? Sorry, just wake you up. Yeah, that's right. That's one of the reasons, right? Because you have a battery. What the battery does? It has a potential difference. It's like a pump. It's like a charge pump or electron pump. It has that potential or pressure inside. If you do not have anything close it, then nothing will happen. If you have something close it, I'm going to pump the electrons outside of the battery to charge up your components on the circuit. So everything is powered up. Okay? So current flows through the component, you get things powered up because you have a battery, and the battery has a potential drop. And that potential drop will deliver the charges to the circuit and make it work. Make sense? Okay. Do you think this is common sense, or do you think this is something you don't need to know? It's good to know, at least, right? All right. Charge, voltage, current. Be clear about these three different concepts. All right, something else. Let me see what I can make you more familiar with this. There's nothing like this, okay? There's no real battery is doing this, okay? But this is, I'm just drawing, so there are different potential levels, and that's the lowest potential in the circuit, which is 0 volts. And here's a symbol for a ground symbol, and you probably will be confused by this a lot if you are not in this. I'm pretty sure a lot of people don't understand what's going on here. What is ground? Is that a real ground? So you can have a floating ground, you can have a real ground, right? Either way. But normally when we are building a circuit on the breadboard, you don't have anything connected to the real ground, the copper bar rate underneath the building. It's just a common reference voltage, which is 0 volts. Because voltages are relative, if you do not have a common, it's really called common ground. If you don't have that common ground, it looks like a 3 volts here, but in the other places, it's probably only 2 volts. So all the voltages are differences between two terminals. So if I say, here is the board, you can build circuits on this board. Okay. For example, we have a circuit here, and I'm using a multimeter to test the voltages at different points. And I test this point, I'm saying, hey, this point is 5 volts. When I'm saying it's 5 volts, I didn't say something, but you should know what does that mean. I didn't say it's 5 volts compared to the ground, but I will just say this is 5 volts. Because 5 minus 0 is 5. Keep in mind, you can have all the voltages are relative. So when I'm saying this point is 5 volts, I'm not saying this is absolutely 5 volts compared to everything in this universe, on this planet. It's just 5 volts compared to where? Compared to the ground on this board. If you have another board, have another ground, you couldn't even compare to there. It's just this 5 volts compared to this ground on this board. But I won't say that every time. I just say 5 volts, 3 volts, 2 volts. Is that clear? Okay. This is 5 volts compared to where? Compared to here. This is 2 volts compared to where? To here. This is 1 volt compared to where? 2 volts in the middle. Important to understand this, okay? All the voltages are relative. It's a difference between two terminals. Or sometimes you can say it's a voltage difference. Let's just write it down here. voltage difference or potential drop. From here to here, how much drop? 2 volts drop. 2, 1. What's the voltage here compared to 5 volts? If I say, what's the voltage here compared to 5? So I'm saying this, you can do a subtraction. If you're a beginner for this, you can think about it in that way, it's easier to understand. So I'm saying, what's the voltage here compared to where? You just use that value minus that value, and you get the correct answer. What's the voltage here compared to 5 volts? -5. So compared to 5 volts, this guy here is -5 volts. Okay. Compared to 3 volts, what's the voltage here? -2. Cool. All right. Ohm's law. Boring?
No, I'm just
So Ohm's law is pretty simple. You got a resistor. So here's a symbol for the resistor. Plus minus V. What does that mean? Plus minus V. Plus minus. Plus means a higher potential, lower potential. And V is what? The voltage drop from where to where? From higher to lower. That's how I label it. That's how we label it. Okay? If I draw a resistor and I draw a plus or minus on the two terminals, and V represents the potential drop from the higher to the lower. So keep in mind, what is Ohm's law? Super simple. You got a resistor, you got a potential drop, and that potential drop will pump current across the resistor, period. If you apply a potential drop across the resistor, it's going to create a current flow through the resistor. Is that clear? What is that? Current. A pretty intuitive way to think about this is water current. It's pretty similar. You can imagine that you got a pipe, you have a pump on one end, as one end of the pump of the pipe, and the other end you are expecting what? Water flow. So do you have a potential difference at the two terminals? You do have, because you have a pump. It's pumping the water through the pipe. Okay? So the potential or the pressure difference of the pipe is similar to what we are talking about, the potential difference of the resistor. Okay, so the potential voltage difference across the resistor will pump the electrical current run through the resistor, and the pressure difference of the pipe will pump water across the pipe, and which can form water current. So this will form electrical current. All right, and there's an equation. It's only one equation for Ohm's law. V over R equals to I. So in that case, you also know V over I equals to R, and I times R equals to V. Right? That's a wire, copper, aluminum, whatever. Do you have a potential drop here? And why? Do you have a resistor? So what's the resistance ideally? 0. According to this, I times 0 equals to what? So what is 0? Current or voltage? Voltage. Is current 0? What is the current? Yeah, V is close to 0, R is close to 0 as well. What's going to happen? Don't think about this in this way. Since, for example, I have this. Probably have done this at home. Have you? You grab a battery and you short the anode to the cathode, use a copper wire. What's going to happen? Super hot. Never try this at home. Okay. You grab a battery, connect the two terminals, use a wire. Not you. Someone. Jack. Okay. Grab a battery, connect the two terminals with a wire. Use his finger, not your finger. Use his finger, and the wire will be super hot. And you can even use that wire to cut a form or paper cut or something. It's going to be super hot. The reason is, do you have a potential drop? Do you have a voltage difference? Do you have a voltage difference? Actually, you have. Actually, the battery has. Since the battery has a built-in voltage potential over here, and the wire is not ideal. It has a super low resistance, for example, 0.00001 ohms, which is R. What's happening here? So V is 1.5, so I equals to V over R, which is 1.5 volts over 0.00001. What's the current? Super high. You must expecting me to calculate this, right? I'm not. High. Okay. But how high? 1.5 over something tiny. It's going to be more than 1.5 at least, right? Remember in the first lecture I told you guys how much current can kill a person? Can kill a cow, not a person. 200 milliamps. And this is already more than 1.5 amps and way larger than 1.5 amps. So it's getting a lot of current, but depends on the capacity of the battery, but actually it's not able to provide that high current. You know, it's just struggling to provide the current because it doesn't have that kind of power. So what's happening is it's not able to provide that current, which is calculated by Ohm's law. It's struggling. It's not that capable. And you have a wire which has a super low resistance. It's going to reduce the voltage potential, voltage drop across these two terminals. That won't be 1.5 anymore. It will be lower than 1.5 and super low, pretty close to 0, because it's delivering a lot of current outside of the battery. This is not a real circuit. Just let you know what's going to happen. Okay, that's the category. Some different category. We just let you know we're not doing this anymore. So what you need to know here is you have a potential drop, you got a resistor, you got a current. And you can calculate current from voltage and resistor, and you can calculate resistance from voltage and current. And you can calculate voltage through current and resistor. So 3 equations. Is that clear? Great. So these are different batteries, for example, you can buy. So these are the voltage readings you can see being printed on the battery. So I'm asking, what are the voltages here? If I'm asking, what's the, wait, this one, yeah, ground, sorry, it's gonna be here. And this one will be here as well. Okay? 1.5. What is this? Ground, 0 volts, always. If you see a ground, which means it's telling you this is 0 volts in the circuit. Here's the battery. What's the voltage here? If I'm asking what's the voltage here, I'm comparing to where? To the ground. So here's whatever designed by the manufacturer for the battery. So this means from the plus to the minus, it has a 1.5 voltage drop. I'm going to say it again. If you see a battery like this, you'll see this kind of label, this voltage rating. That means this battery is able to provide 1.5 volts from the anode cathode. What does this mean? So what does this mean? From the anode to the cathode, it provides a negative 1.5 volts drop. Is that clear? This one, same. From the anode to the cathode, it provides a 1.5 volts voltage drop. From anode to cathode, it provides a negative 1.5 volts voltage drop. So now, let's come back to the first one. What's the voltage here? And how do you calculate it? The battery provides a voltage drop, right? Has 2 terminals. If you want to calculate one of the 2 terminals, you need to know the other terminal. What's the voltage over there? Is that correct? Is there any given voltages? What's that? Ground. Ground is 0 volts, which is given. And I already tell you, from plus minus, it's getting a 1.5 volts drop. So from minus to plus, it's getting a 1.5 volts increment. Is that right? What's the voltage here? What's the voltage here? 1.5 volts. That's why when you use a battery, it's a 1.5 volts battery. That's anode, that's cathode. You ground the cathode, you are getting a 1.5 volts from the anode. That's how you use it. You want to ground the cathode, so you can get a 1.5 volts at anode. You don't have to ground the cathode if you want to create some other different kind of design. But normally, we ground the cathode and you get a 1.5 volts at the anode. So 0 volts here, plus to minus is a 1.5 volts increment. So the voltage here is 1.5 volts compared to where? Compared to the ground. This one. 0 volts here. What's the voltage here? So it's just 0 plus. Is this correct? Because from minus to plus, it's going to boost that voltage. Boost the voltage by negative 1.5. Is that clear? All right. Any questions by far? Feel free to ask. No? What about this one? What is given? The anode is grounded. The anode is grounded. I just ground the anode, right? So 0 volts here. And the battery will provide a 1.5 volts voltage drop from anode to cathode. So what's the voltage here? No. 0 volts here, 1.5 drop. 0 minus 1.5, which is this. Zero volts, drop by okay. So what about this? What's the difference between this one and this one? Huh? Yeah, it depends on how you look at it, right? Same circuit. What's the voltage here? Yeah, 0 volts here. From plus to minus, you got a drop, right? So 0 minus. Okay. Yeah, just start from 0 volts always. And from plus to minus is a drop. It's dropping, right? So 0 minus 1.5 volts, you're getting 1.5 volts here. Clear for this so far, is it? Okay. 1K ohms means 1,000 ohms. What is the current flow through the circuit? So current, so this is just a voltage node. That's a ground node. I ground this point. So 0 volts here. What's the voltage here? Hmm? So is that a wire? Whenever I draw a wire in the circuit, I'm assuming it's an ideal wire. Ideal wire means there's no resistance. The resistance is 0. R is 0. So R is 0 means whatever the current is, you're getting a 0 volts difference, so which means no difference. 0 volts here. What's the voltage here? Is there any resistance over here? No. What's the voltage drop from here to here? What's the voltage drop from here to here? 0. What's the voltage here? What's the voltage here? So conductors will conduct potentials. Okay? You got a wire, you put a potential here, it's going to conduct that potential to the other side. So actually a metal wire, you can make it huge as long as ideal. It's going to be the same potential on that wire, every single places on the wire. You can melt that metal to one metal ball. Same thing, still one voltage node for one piece of wire, as long as there's no resistor on the wire. Only resistors will create potential drop because R times I is V. If R is 0, V is 0. Is that clear? Okay. What's the current? What is the current? Remember Ohm's law, I equals to V over R. What's the voltage difference between this resistor? So what we are calculating is the current flows through this resistor. and this side has a higher potential, this side has a lower potential because of the battery, because here is higher, here is lower, okay? And because this is one voltage node, actually here is here, here is here, same voltage node. So what's the potential drop across the resistor? What's the potential drop from left to right of the resistor? 1.5 volts. So V is 1.5 volts. R is 1 k ohms. The current will be 1.5 milliamps because 1 over 1000 will be 1 milli. So this is literally 1.5 times 10 to the negative 3 amps. So amp is a unit for current. Milliamp is this much amp, 1.5 milliamps. So that's the current. If you know voltage, you know resistance, you can calculate for the current. Okay? Any questions? Feel free to ask. Circuit 1 is not an easy course. It's going to be easy after you are used to it. It's going to be super easy actually. But however, as a beginner, I have seen a lot of people have struggled in this class every semester. So do not feel bad when you are not used to this at the very beginning. It's fine. Okay. I draw the current flow, the direction of the current in this direction, like this, like this. That's the direction of the current I defined. Okay. Is that possible? I can define the current in any direction. I define the current flow in that direction. It may not happen. Because you can see that the potential here is higher, here is lower, and you know in real world it's going to pump current in that direction, which is opposite to this direction I just defined, which is fine because that's a real current. You can calculate it, which is 1.5 over 1K. This is the 1K resistor, which is 1.5 milliamps. You calculate it. So what's the current here? What's the current I defined? I defined the current like this. So what's that current? It's going to be negative 1.5 milliamps. You just define it for calculation purpose. There's no negative 1.5 current flow in the circuit. Is that clear? Okay. But all the times, you actually do not have to consider the polarity all the time. What you need to do is find out the direction of the potential drop or the direction of the voltage and divide by the resistance, you can get a current. For example, I have a resistor like this. This is 1 k ohms. And plus minus is 5 volts. I can say the current flow in that direction, which is the real current direction, is 5 milliamps. That's the current in that direction. So what's the current in that direction? It's going to be negative 5 milliamps. How do you calculate it? You have to calculate using the voltages, the correct voltage direction divided by the resistor. The resistor is just a value. There's no direction. It's not a vector. So I get this value because I use the voltage potential drop from here to here, which is the same direction as the current, to calculate the current. So the voltage from here to here is what? 5 volts. So I'm using 5 volts over 1K. Definitely I'm getting this. If you're calculating the current in that direction, you need to use the potential drop from here to here and divide by the resistor. So what's the difference from here to here? -5. So that's why the current in that direction is -5 milliamps. Okay. I still have a couple. Let me see if you are good enough to do the quiz. No, a few more things. Sorry for that. Okay. Bear with me for another 5 minutes. I'm sorry. More things to cover. Voltages are all relative. What's the voltage here? This is the only given voltage, which you definitely know is going to be 0 volts. What's the voltage here? What's the voltage here? Is it hard to calculate? It's not. Since if I had this one, it's the same problem as the previous one, all the examples I just gave you, right? What's the voltage here? 5 volts, because from cathode to anode, the voltage, the battery will boost the voltage from 0 to 5 volts. Okay. What's the voltage here though? -5. So the question is, this is 5, I understand that. This is -5, I understand that. But is this one affecting this one? Is there any influence from here to here? When you are do voltage analysis, you don't need to look at all these things are confusing you. You just look at the voltage nodes. It's 0 volts, it's 0 volts. Don't worry about anything else. It's 0 volts forever. And the battery manufacturer, the manufacturer tell me it's 5 volts. They have to trust the manufacturer. It's going to be 5 volts. 5 volts, 5 volts forever. So given that, you know 0 volts, you know it's going to boost the voltage to 5 volts. It's going to be 5 volts, definitely. Right? Same here. Okay, a couple of other things. This one. What's the voltage here? What's the voltage here? What's the voltage here? What's the voltage here? And why? Do you have current? Nope, it's a disconnect circuit. It's open. I is 0, right? Is I 0? I is 0. What's the resistance? 1K ohms. What's the voltage drop across the resistor? What's the voltage drop? 0. Why? No current. No current, no voltage drop. So the resistor does need some current flow through it in order to provide you some drop. It's pretty picky. No current, no drop. 5 volts. 5 volts. Is that right? Do you trust this? Do you trust this? Yes, it's 5 volts. Okay. Okay, something else. So what are the voltage drops? V1, V2, V3, V4. What are they? And how to calculate it? Keep in mind, you'll see some similar problems in your quiz pretty soon. So the way to calculate this is use current. So since you know the overall resistance is 4K, is that 4K? So if you put the resistor in series, you're adding up all the resistance in that line. So 1K, 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 so 4K. Okay. So 4K in total. How many voltage? How much voltage? 10 volts, right? What's the current? Overall. What is that? 2.5 milliamps. Okay. Is that 2.5 milliamps? How many currents do you have? How many different currents do you have in the circuit? Is this 2.5 milliamps? Is this 2.5 milliamps? Is this 2.5 milliamps? If you have a one water pipe, do you have one water current or totally different water currents? So this water flows through this part of the pipe and it moves to the other part of the pipe. Is that still the same water? It's still the same water. So it's the same current. So if you have a one wire, it's the same electrical current everywhere. So which means it's one pipe, one water current. Is that 2.5 milliamps flow through this pipe, this part? It is 2.5 milliamps, 2.5 milliamps, 2.5 milliamps, 2.5 milliamps, 2.5 milliamps. Okay? Remember, you are still forming this concept, so never mind. Remember this, okay? One wire, one current. You have two different wires, two different pipes. Okay, so distract that water current, so are getting different current. This is the same current in one wire. So 2.5 milliamps flow through this resistor will create a what? Resistor, current flow through, voltage drop. Ohm's law, right? Resistor, potential drop, current. That's it. Pretty simple, Ohm's law. Resistor, current, then what? Voltage drop. Keep in mind, resistor, current, flow through it will create a voltage drop at the two ends, two terminals. So the voltage will be times 1K, which is, so 2.5 volts, 2.5 volts, 2.5 volts, 2.5 volts. How many 2.5 volts you have? Like 3 stars, right? 2.5 volts, 2.5 volts, 2.5 volts, 2.5 volts. 4 2.5 volts. How much in total? 10 volts. Is that clear? Is that making sense? You got 10 volts overall. You have 2 resistors to drop that 10 volts totally in total. So since they are equal, so every single resistor will share 2.5 volts. It's got one piece of share, one share of the 10 volts for each resistor. So if you are seeing something similar to that, what's the first step? Get a current first. Since you know the current and all the resistance are given, you know the current flows through that specific or every single resistor. You can calculate the voltage drop across that resistor. And that's everything you need to know. All right? We're close. I think we're pretty much done here. You should be ready, I guess, at least. Let's see. Okay, here. The very last one, I promise you. Very last one before you can give me a break. Very last one. Voltage dividers. For example, here's the V out. That's the output voltage of the circuit. That's the input voltage of the circuit. And here's the conclusion. V out equals to V in times R2. Here's the output voltage, output resistor on the top, over R1 plus R2. How do you verify it? You get a current first. So what's the voltage across this R1? So what's the voltage across these two resistors? V in, overall voltage, V in. So V in equals to I times R1 plus R2. V out equals to what? V out is the voltage here compared to the ground, which is exactly the voltage drop across R2. And you know the current flow through R2 is I, the same I. So I times R2 will be V out. Since you know V out, you know V in. So V out over V in. So V out over V in, you just use this one over this, which is I R2 over I R1 plus R2, which is cancel R2 over R1 plus R2, which is V out equals to V in times R2 over R1 plus R2. I promise this is the very last problem I'm going to show you today. I know this is overwhelming, but you have to learn this anyway, sooner or later, or in the department. So it's important. That's a voltage divider theory. Why it's called voltage divider? Because this guy is dividing the voltage into the ratio of the resistance. Why is this making sense? They have the same current. So the resistance of the R2, or let me say this in this way, okay? So listen. The resistance of R2, or the ratio of the resistance of R2 in the overall resistance, equals to the ratio of the voltage drop across R2 in the overall voltage. In short, the resistance share equals to the voltage share. Is that making sense? The resistance share equals to the voltage share. If you have a larger resistance in the same circuit, you get a larger voltage drop because they have the same I. You have that larger resistance times I, you get a larger voltage drop. If a smaller resistance times I, you get a smaller voltage drop. Because they have the same I, So if you use that one divided by this one, you can cancel I. So that's why the resistance ratio equals to the voltage ratio. That's the fundamental of the voltage divider theory. Okay? Makes sense? All right, I'll hand this to you guys, and you'll have a break, and we'll see how that goes. Let me see. I know we still have 40 minutes. Okay? I don't know if we can finish everything in 30 minutes or so. Probably the first three problems. And so anything on the back, let's see. If we don't have time, we don't have to do it. So we have to start, let you guys have that little simple, very brief presentation at 5:20, I guess. Okay, 5:20, so 10 minutes for presentation. And we will have the rest of the quiz to be presented next week. Will that work? I'm not giving homework, right? If you like, you can do it after this class. If you don't like to work with it, you don't have to do it. You can come over next week, and we are going to use the first like 10 to 20 minutes to work on the problem on the back. Okay. And also have a break right now, 5 minutes, hopefully. So we're coming back at 4:55. 4:55. So now you can form groups, 2 or 3. I recommend it 2, but if you have 3, it's fine. And I'm gonna have a little random number creator to pick up which group to present the problem. Will that work? No problem. Okay. All right.